Hi everybody, welcome back to Chem 161. We're going to finish Chapter 1 today, and then we'll talk about the lab, and then we'll start Chapter 2. So, that's a rough order of events. On the screen, I have 3 problems that I don't believe we worked out last time. I don't know if I gave you time to work on them, so whatever. If you've already done these problems, you have the answers. You could punch them in the chat there. But we're going to start here. I'm going to have you do these dimensional analysis problems just for practice. Tell me how much my Harley, which I don't own anymore, weighs in kilograms if its weight is 579 pounds. If I travel 15.5 miles to work each day, how many kilometers is that? And then finally, what would a 2-liter soda bottle be in gallons? Yeah, I no longer have the Harley. I donated it for... I didn't really have a place to store it, I guess I would say. Because where I live now does not have garages or covered parking. I did not want to just sit in the rain. So I donated it. So replace all instances with Harley-Davidson with Jeep Wrangler. And then, well, okay, the mass problem would not work out. There's no way my Jeep weighs 580 pounds. So anyway, do these 3 problems. And we'll go over the answers together in about 5 minutes. So see you in a bit. One more minute and we'll go over the answers. All right, let's go over the answers here. I have a cat here, but she isn't saying anything. She's being very quiet. Hi, Maya. She must rub her nose against everything, because that is what cats do. So she's brushing against the armrest. Now I'm just petting her. Now she's on my lap, so... Alright, well, I'll do the best that I can to do these problems here. With a cat on my lap. There we go. That's what I want. I didn't zoom this in. Alright, so I have a 579-pound Harley. What is its mass in kilograms? So, my, this is going to work. I can't write with you on my... Go in your bed. Go in your bed. Sorry, I'm dealing with a cat. Maya, go in your bed. Maya, go in your bed. Yeah, go in here. Yeah, go in your bed. She's just sitting there meowing at me now. Oh, cats. Alright. For this first problem, I want to turn this from pounds to kilograms, so I'll set up my units such that the pounds cancel out, leaving me with kilograms. And then I need a conversion from pounds to kilograms. And I believe that that's right, but let me look it up on Google anyway. 1 kilogram is 2.205 pounds. Okay, cool. 579, 2.205. So I get 262.585. I only get 3 sig figs, so I'm going to write down 263 pounds. Sweet, there you go. Oops, hold on. Hold on, I wrote the wrong unit. Wah, wah. Kilograms. I was like, wait a second. That seems really light for a Harley. I weigh more than a Harley? Are you kidding? Actually, I'd weigh almost exactly the same as a Harley. Okay, that was number 1. Number 2. I definitely do not weigh the same as a Harley. You've been using 2.21, that's fine. The issue will arise if, like, I gave you a number that had more than 3 sig figs. You don't want your conversion to be the limiting factor for sig figs, because it will lower your precision, and then the error on your answer will be larger. So if you use 2.21, well, let's see what you would have gotten. You should have gotten the same answer. 262. Yeah, that's close enough. Remember, that last digit is your uncertain digit. So that would be this digit right here. The last digit is uncertain. It's going to be like plus or minus 1 anyway, off the right answer. So I can't tell you that 263 is the right answer. I don't know. It could be 262. Like, who knows what the actual weight of it is? We would need an infinite number of sig figs to find out. So, but either of those answers is close enough to the actual answer, whatever it is. So I would accept either. All right, I travel 15.5 miles to work, or at least I used to when there wasn't a pandemic, although I am driving to work tomorrow for the first time in forever, because I have a hybrid class that meets on Friday. So that's going to be strange. All right, I want to turn miles into kilometers, so we'll set up the unit. It's not kilograms, but kilometers. There we go. We'll set up the units so that they cancel, and then let's look up 1 kilometer to miles. All right, so 1 kilometer is 0.6214 miles. And 15.5 divided by 0.6214. I got 24.9. I accidentally decimaled when I didn't mean to. $24.9. Wow, I am just the worst at units today. Holy fuck. I'm just going to write down whatever units I want today, you guys. That's what I've decided. All right. Kilometers. Yeah, I'm writing down whatever unit I'm thinking of, and then I look at the problem for what unit I should write, and then I'm like, wow, I've done the same mistake twice. I'm dumb. I think I just need more water. That's what I should do. So I apologize for that. Let's do the third problem. I got to put that on the screen, though. So first, let's turn this into gallons. So I have a 2-liter soda bottle. So I want to go from liters to gallons, and that conversion exists. There's like 3.5 liters per gallon or something like that. Let's find out. 1 gallon, 2 liters. Is that that's not the US liquid gallon. There we go. Okay. If you are doing this on Google, I want to show you this because this comes up a lot, and I always initially get fooled by this. I'm like, wow, that's a lot bigger than I expected. But in reality, it's not. There's an error. Okay. So if you're typing in things on Google and you type in like gallons to liters, the default one that they list is gallon, but that's not the same as the US liquid gallon, which is what you want. So this is the default, and you'll notice you get a weird number. And what you want is the US liquid gallon, which gives you the correct conversion. Okay, so be mindful of that, specifically 4 liters to gallons. Google will give you the wrong number initially, and I have no idea why. Because there's certainly 1 gallon that is... Oops, I can't use my stylus to move this window. There's certainly 1 gallon that is used the most, and it's not that one, as far as I'm aware. So 2 divided by 3.785. And so I get 1 sig fig for this, so I get 0.528, whatever, becomes 0.5 gallons. And then to turn that into microliters, there's my units that cancel out there. A microliter is 10 to the minus 6 liters. There you go, easy as pie. All right. So hopefully we were able to do those. These are very basic problems that are reviewed for 140. So let's start asking some more complex problems. So you've been seeing that on these over here, I've been trying to... I didn't do it for the last problem, but I've been writing out like the blueprint in red. So I call this a unit map. Unit maps are helpful for plotting out what you need to do to solve a problem. If you aren't sure where to go, just draw every possibility you can think of and see if you can connect where you're starting to the goal. So, for example, let's suppose that I had this problem here. Well, oops, that's the wrong slide. Sorry. So, for any given problem, if you are given a starting point and an ending point, and you're like, I don't know how to connect the two, here's a strategy that you can use. So, for instance, I need to connect hours to years, because if I can make an unbroken chain that turns hours into years, I can then solve the problem and figure out how many hours are in 2.0 years. Now, there's all sorts of things that you could do with hour. You could turn this into minutes, which can then be turned into seconds, but that's not going the right direction, right? I could turn hours into days, and days I can turn into weeks, and I can turn days into months. But not every day is this, or not every month is the same number of days, so doing something like months into years doesn't really work. But if I did this, now I have a path from the starting point, which was here, to the end point, which is years. So if I turn hours into days into years, I can solve the problem. These other paths are dead ends, but I could use them for other conversions. So if you are writing out all of these different paths on like a little blueprint, this can help you figure out what you need to convert your units to. And at first, that's probably the hardest part of the problem, is trying to figure out, okay, how do I turn this thing into this other unit that I'm being asked for? Because you're going to need to know which conversions are which for the problem you're using. So we already know how to do hours per day. There's 24 hours in a day, and there are 365.25 days in a year. Why 365.25? Because a leap year, right? I didn't put enough space for my decimal point. I just realized we're going backwards, so I actually I want to start here instead and go to hours. So I'd cancel my units out that I don't want, and then I'd fill in the correct conversions. So in 1 year, there are 365.25 days. And then in a day, there are some number of hours. 24 hours in a day. So how many hours would there be in 2.0 years? There would be 17,532, which when I do sig figs rounds to 18,000 hours. All right, so my blueprint here helped us do that. Now you can blueprint any units that you want to. And when you are given different conversions, it becomes easier to see how to use those if you have the blueprint in front of you. So I'm going to leave this problem for you to try. If I drive 75 miles an hour down the highway, how many minutes will it take me to drive 20 miles? Now, if you're a police officer or you work with any form of law enforcement, you're going to use 55 miles an hour for this problem instead. For the rest of us, 75. One quarter, I did actually have a cop in my class, and when she saw this problem, she laughed. I was like, all right, you have to solve it with 55. And so she did. She used 55. I was like, I'm legal. I'm not confessing to me doing anything. But no, seriously, I drive, like, fast. I have places to go. So tell me how many minutes it'll take me to drive 20 miles. One more minute, we'll go over the answers. All right, let's go over the answer here. So for this problem, I have a distance. That's in the wrong color, I realize. I'm given a distance that I want to travel. And I want you to tell me how many minutes it will take me to go that distance. Well, I don't know how to convert miles to minutes, because one is a length and one is a time, right? I can turn miles into hours, though, because I have that conversion. That's handy. So in 1 hour, I would go 75 miles, because that's how fast I'm going, yeah? So if I know how many hours I'm going, now I can figure out how many minutes I'm going, because in 1 hour, there are 60 minutes. So let's do all of those conversions, and let's see here. We're going to go 20 miles. We're going to do the conversion just like you see them up top, except I might have to flip these around or whatever. So miles per hour. I'm going 75 miles per hour. So there we go. And then I'm going to turn hours into minutes. Cancel out the units I don't want. And there are 60 minutes in 1 hour. And when I do all of that, should get 16 minutes, but let's see. 20 times 60, 75. All right, how many sig figs should my answer have? Well, this has 3. 2. This is exact. And this 1 is also exact. So I should only have 2 sig figs. So this goes away. 16 minutes. All right. For the next problem, we have a puppy. This is Scoots. Scoots eats 65.3 grams of kibble every day because he is hungry and growing. How much food will Scoots have eaten in pounds in 35 weeks? He's a hungry growing boy. We need to go and buy enough food for him. However, we can only go to the store once every 35 weeks, I guess. I don't know. So, what size of bag will I need, assuming that he eats this much food every day? Go ahead and solve this, and we'll go over the answer in just a second. All right, 1 more minute for puppy. All right. So for this problem, we have, oops, hold on. Let's recenter this. We have an amount of time. So we have weeks. And in that number of weeks, I want to find out how many pounds of food he can eat. Well, I know how much he eats per day, right? So if I can turn this into grams of food, and there's a relationship between grams and pounds. I'm sure that's out there, right? Well, if I know how many grams he eats, that would be the number of days. Because he eats a certain amount of grams per day. And then we could say, well, I know the number of weeks or days there are in a week. So we're all set here. So there are 7 days per week. Each day he eats 65.3 grams of food. And then 1 pound is 453.6 grams. So those are all conversions we can either look up or are in the problem itself. So now we can solve the problem. So 35 weeks, we'll turn weeks into days. There are 7 days in a week, so that's all set. Then we'll turn days into grams of food. He eats 65.3 grams of food per day. And then there are 453.6 grams per pound. That's going to tell us how many pounds of food we need to buy for our puppy. And I get 35.2700, which becomes 35.3 pounds, working on the assumption that weeks are a counted quantity. If they are, then this number right here becomes our limiting for sig figs. Because 7 days per week is counted. 1 pound per 453.6 grams, that's 4 sig figs. So I would say 3 sig figs is okay for the answer. But if you put 2, that's also okay. Because it's unclear. You can count weeks. You can go to your calendar and just say, okay, 1, 2, 3, 4, 5, etc. But are they full, complete weeks? The problem isn't very specific on that. So either of those answers would work for this. I would accept 2 or 3 sig figs. But roughly, your puppy is eating a pound a week. Oh, excuse me. He's just a little guy. All right. Let's get Hazel out here. There's Hazel. Hazel's a kitten, and Hazel is at the vet because she has injured her paw. The veterinarian recommends that we administer a solution of aspirin for her to deal with the pain. The recommended dose of aspirin for a kitten is 3.67 milligrams of aspirin per kilogram of kitten weight. If Hazel only weighs 2.41 pounds, how much should I medicate her so that she experiences pain relief? Please do not overdose my cat. This is not actually my cat. But I would adopt her because she's so cute. Look at her. All right, solve this problem and we'll go over the answer. And then we're done with these problems. We'll go on to chapter 2. All right, one more minute. We'll go over the answers here. All right. Did you overdose my cat? I hope not. Oh, I didn't play the sound effect. Oh, no, we got to do that again. Let me try this again. Did you overdose my cat? There we go. Oh, it turns out somebody did overdose my cat. Sigh. All right, well, let's see what the answer is. We'll go over here. So when I wrote that slide, I actually did have a cat named Hazel, but she passed away. She was not a kitten. She was like 23. She lived to be like the oldest cat, and everybody loved her. So we have pounds of kitten. Hazel lived a long and wonderful life. I adopted her when she was like 19, apparently. She needed a home, and I was like, well, I don't have a cat. I'd love a cat. All right, and I want to find how many milligrams of aspirin. Aspirin, I guess, is what we're going to give her. That's like budget aspirin. Aspirin. There we go. All right. So I need to know what her mass is in kilograms. Because I know how much milligrams of aspirin I give per kilogram of kitten that I have. And so The conversion from kilograms to pounds is just 2.205 pounds per kilogram. And because these are kitten, I'm just going to write it for both. Why am I writing the kitten label here? The reason is all of these things use mass, and I don't want to get them mixed up, right? Because right here, for kilograms kitten and milligrams aspirin, for every 1 kilogram of kitten you have, and my Photoshop isn't registering each keystroke there, or pen stroke, I can give 3.67 milligrams of aspirin. So, because these are both masses, I don't want to write just milligrams and kilograms over each other, because that doesn't make any sense. There's way more than 3.67 milligrams per kilogram, but we're using it in a different way, so it's important to have these delineators here. All right. Hazel weighs 2.41 pounds. She's a little tiny thing. And we'll put the kitten in there just to make sure that we get our units straight. All right, so we're going to cancel out pounds of kitten. And for every kilogram of kitten, that's 2.205 pounds. And then kilogram kitten and milligram of aspirin. And for every kilogram of kitten, you may administer safely 3.67 milligrams of aspirin. And so when I punch that into the calculator, I get 2.41, 3.67 divided by 2.205. And so labeling all of your masses properly is very important. You want to make sure that you are not accidentally mixing up which ones are for the kitten and which ones are for the aspirin. That analogy is when we're going to start doing stuff like grams of chlorine to moles of chlorine to moles of any other thing to grams of the other thing. And so you're going to want to write out all of the different units for each thing and be as thorough as possible so that when you look back at your calculation, you don't immediately go, what the hell is going on? All right. All right. There's Hazel. Oops, that's not Hazel. There's Hazel again. All right, bye, Hazel. See you next time we do that problem. I'm going to leave these practice problems for you to do. There are 3 extra ones here for you to do. This is apparently when I was playing Dragon Quest IX, I wrote this problem. So 3 extra problems down at the bottom to practice on your own. I'm going to skip those. I'm going to do the very quick temperature rundown. Temperature is not something that we're going to really be using that much in this course. Temperature is going to be much more relevant to you in 162 and 163 because you're going to be actually using formulas that invoke temperature. The 3 units of temperature that we care about in this course are Fahrenheit, which is good for confusing Canadians. Why isn't this? Oh, because I'm not clicked on the right thing. There we go. And then Celsius and Kelvin are used in the laboratory. Now, there are some interesting things that arise from this creation of the scales in these manners. So, for example, the interval between the freezing point of water and the boiling point of water is 100 Celsius and also 100 Kelvin. So 1 Celsius and 1 Kelvin are the same thing. But of course, Fahrenheit, there's 180 intervals here. So 1.8 Fahrenheit equals 1 Celsius. Because Fahrenheit's got to be stupid, right? There's also another reference that we care about way down here at the bottom here. And so that is where we have 0 Kelvin and minus 273.15 C. And this is like minus 454 or something. Nobody gives a shit about Fahrenheit. I even wrote the 4 as an F there. Minus 454. So what this temperature range down here, this is called absolute zero. The reason that we care about Kelvin as a temperature is that for the definition of temperature, we describe temperature as molecular motion. And if we have a point where molecules are not moving at all, they have no kinetic energy at all, they are completely stationary, we would call that 0 Kelvin, or absolute zero. Now, it's not possible to get to absolute zero in practice. In theory, it might be, but in practice, that would require you to have a perfect insulator and insulate stuff from the outside world using that perfect insulator. Now, the reason that we use Kelvin is because in formulas, if you have a temperature term, so for example, if I have something like this, and I am inputting a number for temperature, I can't input a 0 value. That would blow up my equation, right? So there's nothing below 0 Kelvin. That's correct. By definition, because we have defined temperature as the amount of molecular motion there is. If a molecule moves in reverse, that doesn't mean that it has negative motion. That just means it has positive motion in a different direction. So 0 Kelvin would be no molecular motion at all. Now, if you go looking up this information on Wikipedia, what you're going to find is that, wait a second, you can get a negative Kelvin. But that is actually using a different thermodynamic definition of temperature, which is, I want to say, enthalpy over entropy, or delta H over delta S. And there are very unique circumstances where for specific systems, you can actually get a negative temperature. And the negative temperature in Kelvin is actually hotter than infinity degrees Kelvin, based on that definition. So, you can technically get negative Kelvin, but not in the way you think. Believe it or not. But that is a whole rabbit hole that we will talk more about in 163, if you remind me. Because we will formally define temperature with respect to enthalpy and entropy. So for our purposes, you can't go below 0 Kelvin. So you're never going to input 0 Kelvin into a formula, because we're not going to do calculations at 0 Kelvin. But 0 Celsius is a very reasonable temperature. That's a temperature that you could feel by just going outside, like, say, last night. It is so freaking cold outside, and I hate it. Where is spring? I want spring. That day that was 70, bring it back. I want some of those before all of the sky is on fire. We know it's going to happen. That's August in the Pacific Northwest. Grumble, grumble. So those temperatures, only one unit can actually be used in formulas, and that is the Kelvin scale. Because Kelvin scale is set with 0 at the very, 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 very bottom, which is impossible to reach. So therefore, all of our formulas should work with it, because we're not going to be working in that range. Celsius, on the other hand, is more convenient for our conceptualization of temperature, because we have set 0 and 100 to very meaningful things, which are the freezing point and the boiling point of water. Excuse me. Fahrenheit is just useless, so it can go just be dumb. I don't know. Now, there is a fourth temperature scale. Celsius and Kelvin are related to each other in the same way that Fahrenheit and this other temperature scale are related to each other. In the sense that this down here would be 0, and then the 0 point of Fahrenheit is whatever Fahrenheit would be. So, well, now we need a letter for this. Does anybody have an idea what letter I should give this? Anybody know what letter that I should give this other scale here? Here, I'll give you a hint here. We're missing a letter. Oh, way to blow the joke, Owen. You went straight for the correct answer. Yeah, that's a better choice, but unfortunately, R is correct. There you go. That was the right answer. So R is called the Rankine scale. And the Rankine scale is basically absolute zero for Fahrenheit. It will probably never come up. I just like to make the FUCK joke because it is entirely fortuitous that the only letter missing in the 3 temperature scales is the vowel. Like, you can see it right here. Where's my highlighter? There it is. Like, somebody knew what they were doing when they named these temperature scales. So, here are the formulas for turning temperatures into one another. A note that I will give you, we're not going to actually do this because you could just make Google do it, is that for these formulas up here, everything is exact. So the 32 and the 1.8 are exact. You might actually see the 1.8 written as 9 over 5. This divided by 1.8 over here is actually 5 over 9 when multiplied. So you might see a scale. It's like times your Celsius by 9, divided by 5, and then add 32. And then do the opposite. Subtract 32 from your Fahrenheit, then multiply by 5 and divide by, or whatever. And it's just, I've changed it to 1.8 because it's easier to typeset a decimal. This formula down here is inexact because we are measuring the Celsius scale against the Kelvin scale by sliding it down some amount of degrees. And the way that we know how far to slide it down is that we have extrapolated it using a formula, which we can calculate absolute zero with. So just be mindful of that. Kelvin and Celsius, the conversion between those is inexact, and so you could have more sig figs past this. Generally speaking, you won't need past the hundreds place. Alright, I think that's everything. Oh, we already talked about absolute zero. We'll talk about absolute zero more next quarter. I'm not going to make you do these exercises because, you can make Google do it. There's your chapter summary. You could read over the chapter summary if you want on your own. It's in the slides. We are instead going to take our break. Alright, I'm going to go get the Chrono Cross music back up and going. I'll see you in 10 minutes. You know, if I can find the track that I'm looking for. Hey everybody. Alright. We're going to start on Chapter 2 now. So I have the Chapter 2 slides up here. Chapter 2 is a bit about the history and discovery of the component parts of atoms and what we can do to manipulate those parts in various ways, as well as gain some understanding of what those parts do. Where's the orc and the music at the end of Chapter 1? I don't have that for my 161 slides. I actually changed it out for 161, and then I put it back for 163. So, yeah, no celebratory orc at the end of my slides, which is kind of obnoxious. I might have to go back and fix that. All right. The first thing that we're going to do for Chapter 2 is we're going to talk about very, very, very fundamental topics and ideas of how people came up with this idea that, you know, I bet matter is atomic, because it wasn't always like this. In fact, the first idea that ever came about was that of this guy named Democritus. So, Democritus was a philosopher in ancient civilization. This is around the year 400 BCE. And the legend is that he was down at, like, the shoreline, and sand was sifting through his hands, and he thought to himself, you know what? If I were to split this particle of sand into pieces, I would eventually get down to a piece so tiny that I would then split that in half, and it would no longer be whatever sand is. It would be something else. And he decided to call that tiniest particle the atom. Well, he called it atomos, which we call atom. So he thought matter has a finite endpoint. You can only divide it so far. There must be some smallest block of matter. Now, along come Plato and Aristotle, and they thought Democritus was just off his rocker. And so they decided that, no, that's ridiculous. Matter must be infinitely divisible. You could split anything you want to in half over and over and over and over again. That's what our mathematicians tell us. Now, how did they determine this? Well, they got high on opium and drank wine and then thought about it. And then that was the conclusion that they came up with was, well, if I can divide numbers by 2 over and over, surely I can divide matter by 2. Oh, Aristotle, you're so smart. You should write a book about this. And so they did. And we later found that that was wrong. The correct answer was Democritus, with his idea of, hey, matter does have a smallest unit to it. And that idea of the atom persisted toward civilization's understanding of matter up through today. Now, the true moral of the story here is that Greek philosophers are stupid. Nobody did any experiments to verify any of these hypotheses. All they did was think about it. So what they were doing was essentially hogwash. It would be like if I taught you this class and I showed you no evidence of anything. Like, we didn't do any labs to show that this stuff actually happens. And all I did was just, like, say, okay, this is true. Now, alarmingly, I do a lot of that. In fact, most instructors do. We don't prove everything to you. Have you ever taken a math class where you have proven that 1 + 1 = 2? It turns out that that is very, very difficult to prove. We just assume it. However, I do assure you that I am making these lectures in good faith, and that the information that I am providing you is either intended to be true, or I am holding falsehoods from you because it simplifies the matter so that we can understand it, and then later on we will learn what I have hidden from you, basically. But these guys did not make any experiments. They basically just thought that this was the case, and then that was it for about 2,200 years, until this guy came around. This is John Dalton. John Dalton published a pamphlet or article with a very important treatise on what he called the atomic theory. Now, before this time, most people didn't really know or think about the nature of matter. And so everybody was just basing all of their experiments and all of their understanding through the Renaissance era on the classical theory of the four elements. So those were fire, air, water, and earth. Now, Dalton came along and he actually did several experiments to try and understand how matter behaved. And he came up with several postulates that we're going to show on the next slide here. And so this is called the atomic theory of matter. And so here are the 5 postulates that he proposed. So the first one is that matter is composed of atoms. The smallest unit of matter is called the atom. It is the smallest particle that can participate in the process of chemistry. If you use only smaller pieces, or like you try and split this object into smaller pieces, this atom, you're not doing chemistry anymore. You're doing nuclear physics. So in chemistry, atoms can participate in chemistry, and they are the smallest particles that can. We're going to learn that there's a little bit of an error with that statement, but again, remember, this statement was made in like the 1800s. Number 2, all atoms of a given element are identical to one another. For instance, any copper atom in a sample of copper is exactly identical. Again, we're going to find issues with this in just a little bit. But for the most part, he's on the right track. If you have different elements off the periodic table, they must be different from each other in some fundamental way. For instance, a copper atom and a zinc atom will have some difference in their nucleus, in their electron cloud, in their something. They have to be different somehow. And we're going to show that in a little bit. Number 4, if I combine atoms together to create a compound, I always have to have a whole number ratio. What that means is that the following would be valid. So something like this. If I combined a carbon and 2 oxygens, 2 times oxygen, I could make this. That's valid. But I could not combine 1.5 oxygens to get CO 1.5. That's not okay. You cannot have fractional atoms, is what number 4 is saying. And then finally, number 5, you cannot transmute elements into other elements. A carbon atom will remain a carbon atom through a chemical reaction. You may not turn the carbon atom into a hydrogen atom, or a helium atom, or a nitrogen atom. That is not a chemical reaction. That is not something that happens. All you are doing is rearranging the substances. Now in Chem 163, we are going to talk a little bit about transmutation, because transmutation is a thing that happens. Elements can and do change from one element to another through the process of either fission or fusion. For instance, you could take 2 hydrogens and jam them together under a lot of heat and pressure, i.e. in the center of a star, to create helium, and you get energy from that. Likewise, you can fission uranium into lighter particles by hitting it with a neutron and it splits in half. So, those are examples of cases where number 5 is false, but as far as chemistry is concerned, number 5 is true. So, we can poke holes in several of these. Number 4 is pretty solid, but it's kind of the only one. 3 is pretty solid too, actually. You cannot make 2 things, you cannot make 2 atoms be exactly identical, but be of different elements. But 1, 2, and 5 we definitely poke holes in, and we're going to discover that as we go through the period today. Now, Dalton's postulates are very important because at the time, when he was doing his experiments, he was realizing that a lot of the reactions he was doing didn't really make sense in the context of there only being 4 elements. Like, what element would copper be? Is it, like, mostly earth and a little fire because it's red? Like, what does that even mean? Is oxygen air? But you can burn it. So he threw all that out, and he said, okay, if I have elements such as copper and oxygen, the matter and how they interact with each other must be particulate in nature. Because if I do a reaction, like as shown here, so I have copper reacting with oxygen to create copper 2 oxide. But if I were to reverse the reaction, I would get the substances back again. Like if I were to heat this and heat the oxygen out of it. Some substances, if you heat them or you pass electricity through them or whatever, decompose into simpler substances. Those simpler substances must be atomic in nature once you have gotten them to the simplest possible outcome. That was what he postulated. He said, if I want to turn this stuff right here back into this stuff... Wow, I don't know what happened with my cursor there. If I want to turn one of the combined stuff back into the individual stuff, I just fill it with energy. Well, if it was only one substance to begin with, why would it break down? So he postulated that if stuff is breaking down, it must be particulate in nature, and therefore atoms must exist. Now, this follows the conservation of mass, because no atoms are created or destroyed. All we're doing is rearranging them. Now, Dalton worked with some other chemists. Here's an example of one of them, Joseph Proust. And the quantitative information that came about from these studies was used to help solidify some of those postulates that we just took note of. So the first report, that I guess we'll call it, that helped Dalton come up with these postulates was Proust's idea of what was called the law of definite proportions. And the law of definite proportions says this: the ratio of masses of elements in a compound is the same, regardless of where you get that compound from. Now, on its own, that statement doesn't really mean much. But what this is saying is that if I have this compound, AB, and I split it into A and B, and I weigh the amount of A and the amount of B, and then I take their ratio, I will get a number. And regardless of which AB sample I get from wherever it is, I will always get this number when I do this process. In other words, all carbon dioxide is the same, whether I breathe it, you breathe it, someone else breathes it, etc. Because the ratio of grams of C per grams of O must be the same. So let's look at an example of this. I'm going to take 2 samples of gas, and I'm going to decompose them. I'm going to pump them full of electricity so that I break all the bonds. I am then left with just the elements, and those elements give me the following masses. I get 1.16 grams of carbon, 1.55 grams of oxygen. Then I do the same thing for a different sample, and I get this ratio. And so the question is, are these samples identical compounds or are they unique? Are they different substances? So let's go over here. And that didn't show up. Hold on. And let's see if we can answer this. So since I have more oxygen than carbon, I'm going to make the ratio of of oxygen is what I wanted to say, to carbon. So let's look at sample A. So sample A, I have 1.55 grams of oxygen to 1.16 grams of carbon. And so if I do this ratio, or ratios are just fractions, so... Oh, for fuck's sake, calculator. 1.55, 1.16. There we go. I get a ratio of 1.33 grams of oxygen per gram of carbon. Now let's look at ratio B. Here I have 3.33 grams of oxygen per 2.50 grams of carbon. And we'll take that ratio as well. And I get the same ratio. And so the conclusion I would draw from the law of definite proportions is that these are the same substance, because they have the same ratio of masses of their elements. Now, it turns out that this is not 100% accurate. However, if you are given these masses and you know nothing about anything's chemical formula, this is as sure as any a good starting point, right? So these rules were used and utilized in an era where chemical formulas didn't exist. Nobody knew what CO2 was, nor did they know what H2O was. They just called them water, and for CO2 they actually called it phlogiston. You can read all about that one. But yeah, they did not have any formulas. They didn't know what any of these things were. The periodic table had not been invented yet. And so they had to do the best that they could with very little information. And so that's where they came up with this idea, was the law of multiple proportions. All right. I'm going to give you a third sample here. And what I want you to do is, for this third sample, where I have 3.82 grams of carbon and 10.18 grams of oxygen, I want you to tell me if sample C's ratio, what it is, first of all, for oxygen to carbon. And then tell me, is it the same as samples A and B, or is it unique? So I'm going to give you 3 minutes to punch this in the calculator. We'll go over the answers in just a second. All right, we got some answers coming in. So you guys got 2.66. Let's see what I get here. I'm pretty sure you have the right answer, but we'll show the calculation here. That should be an oxygen, sorry. So O and then 3.82 grams of carbon. And so when I punch this in the calculator, I'm definitely not going to get 1.33. So this substance is not the same as A or B. It is unique. Now, interestingly, you might notice that there is twice as much oxygen in the sample per carbon gram as the previous one. So if we wanted to, say, predict what the formula was, we might be able to use this for some helpful circumstance, right? Because if I have a ratio that these ratios are off by a factor of 2, right? I'm just taking this one, I multiply it by 2. That sure tells us something about it, right? Must be twice as many oxygen atoms in the formula. And that's where this comes in. The law of multiple proportions says a bunch of words on the screen that in the formal definition doesn't make any sense. What the law of multiple proportions says is that if I look at these ratios that we just made back here, that I underlined, and I compare them, I should get a whole number. That whole number is going to be our multiple, or our multiplier. So let's do this. Let's take those ratios that we just got, and then we'll divide them by each other, and we should get a ratio of small whole numbers. So let's do that. There's sample A and B and sample C, and we found that the multiplier was 2. And the way that we got that was we just divided these two, right? It's 2 to 1. Our conclusion is that sample C has twice as much oxygen in it as samples A and B do. And from there, we could say, well, okay, I'm going to just assign sample A to be CO. Therefore, sample C must have been CO2. Now, this is an assumption, because our 1.33 grams oxygen to 1 gram of carbon could be really anything. But if it is CO, then sample C must be CO2. And so you can see how these two laws that were proposed, the definite proportions and then multiple proportions put together, can help you start to slowly figure out what chemical formulas are for any substance you do experiments on. So this is super useful, and because we have got formulas for virtually everything today, we no longer really need it. So this is basically ancient technology. This is obsolete. We now have many, many better ways to figure out the formulas of things, but it's nice to look back at history and see how far we've come. So, do you need to know this for this class? Yes, technically you do, because the end exam, when you get to all the way to the end of 163 and you take the ACS exam, they're going to want you to know what Dalton's atomic theory was. So, you do need to know these slides. This is more than just a curiosity. All right. I'm going to give you this practice problem. Let's suppose that I give you X and Y, and when I decompose them, I get iron and oxygen out of them, and these are the ratios of masses that I get. Or I'm sorry, not ratios, but these are the masses of substances. What I want you to tell me is, are X and Y unique, or are they the same compound? And if they are different, what is the ratio of difference between them? So give it a shot. We'll go over the answers in about 3 minutes. One more minute, we'll go over the answers. All right. So let's go over here. We're going to do this sort of process again. All right, got sample A. And so I'm going to take mass of iron divided by the mass of oxygen. And that's going to give me a ratio of iron to oxygen. I got 2.33. Actually, I get to do 4 sig figs, don't I? So all right. So there's sample A. Let's look at sample B. So for that one, I get 3.490 grams of iron per oxygen. So we already can tell that these are unique. And if I find the ratio between these ratios, so if I do this, what do I get when I do that? You'll notice I get 1.5 to 1. So what that means is, so this is B over A here. So what that means is that whatever formula I have for A, I would have 1.5 times that much iron in sample B per gram of A. Now, that makes some interesting consequences here. So if I say that A is just this, then B would be this, but that's not possible. This is what actually is implied by that. So definitely not the same compound here. In fact, Fe3O2 doesn't exist. I'm just making it up. But the point here is that you can use these two rules, or laws, I guess we'll say, to determine the formulas of things, provided that you are making some assumptions about the simplest one. Because at some point you have to assume that you have to assume a starting point. All right. That's our brief history of the atom. Let's take that in the last 20 minutes here, and we're going to look at some experiments that were done in order to revolutionize the idea of what atoms are, because for a long time, people didn't have any idea. It took up to the 1800s to even understand that atoms existed in the first place. It'd be another 150 years before people figured out what was in them. So after the year 1800, people asked that question. That was the next topic, was, okay, what are atoms made of? And what makes an element different from any other element? And so the first experiments that were done were only, it was like the late 1800s when this happened. So it was many years, 60, 70 years after Dalton, before we even started to like scrape away at the surface of what is underneath the atom. And so this is J.J. Thomson. J.J. Thomson devised this device called a cathode ray tube. And what it looks like is the following. I got to zoom in on this. Oops, that's not how you zoom in. On each side of the tube is like a... Oh, I can't draw on this. That's right. Okay. There's like a... that's not where I want to point. I want to point right here. There we go. There's a little plate at each end of the tube. It's hard to see here, but those plates are connected to a electrical line, which is then connected to a battery. And those plates provide a space for an electrical beam of particles to go across the chamber in front of this fluorescent screen. So the screen is just painted on the side or placed in the tube so that you can see that there are things hitting it. And what this does is that when you apply a high voltage, particles beam from one side of the container to the other. Now, that's cool and all, but the interesting feature about this is that if you stick a magnet next to it, the beam gets diffracted. Or deflected. Sorry, diffracted is something else. It gets deflected into the wall, and then the electrons eventually funnel over to the other side because that's where the potential is. Now, why do these particles bend like this? Well, it was known that things that carried a charge would interact with a magnetic field. So the particles that were involved in this process that were coming off of these plates must have a charge. And they called that charge the electron because it was derived from electricity. When I create this electrical current, I can observe the electron. And so that's where the name comes from, presumably. And I actually have a demonstration of this that I'm going to show you on YouTube, if I can get the video to load. This video is no longer available because the YouTube account associated with it has been terminated. Oh no! So now I have to find another cathode ray tube experiment that isn't terrible. That's gonna suck because I particularly liked that instructor because. All right, this one is only a minute long, so we'll try this.
This is a...
Oops, sorry. Hold on. Let me get rid of the audio here. There we go. You know, I should just make this smaller. Hold on. All right. This is a cathode ray tube, and you can see the plates, which are roughly about here and here. Now, inside the tube, it is evacuated so that there's a very low pressure of air in there, like almost zero. And so what he's going to do is he's going to switch this on at the electrical source. So whatever battery or voltage that is being applied, looks like it's being plugged into the wall. And so you can see the beam being cast across it, and he's using this magnet to deflect the electrons away from it. Now, the screen that's in place here is literally just because when electrons hit it or strike it, you can see where they are. But really, all this is saying is that, okay, an invisible stream of particles is going across from one side, this is the source side, to the other side. And so what that means for us is that there must be a charged particle going across the tube. But what does that mean? Okay, there is a charged mobile particle in an atom. That's interesting. I wonder where we can go with that. And so that's where the oil drop experiment comes in. So Robert A. Millikan did the oil drop experiment in 1909, and his experiment was actually a little bit more complicated. And I do have a video for this too. His idea, I'm not going to be able to do this without drawing on this, so I'm going to have to zoom it out real quick, was that, okay, I'm going to take individual oil particles and just have them drop down through this hole. And if I can stick something that has a charge on them, then it will interact with this charged plate somehow. So this is more or less what was happening. So he had his oil particle and then his negatively charged plate. And so he said, okay, if I find out what the charge on this object is that's on electron, or that is the electron, I can figure something out. If it's positive, this is just going to accelerate into my plate. But if it's negative, something interesting will happen. And that interesting thing is this. I will have a drop of oil that will accelerate in the opposite direction because it will be repelled by the electric field of the charged plate. But if I can turn the electric field to a very specific magnitude, I will be able to exactly counterbalance the force of this falling due to gravity. The force of this being pushed upward is equal to the charge that is on this particle times the the electric field. The electric field is this down here. And so what they did was they said, okay, well, if I get this electron to just this oil droplet to perfectly balance so that it is motionless, then these forces must be equal. And so that must mean that QE equals mg. We know what gravity is. That's easy. We know what the mass of this particle is, or we can at least solve for it. We know what the electric field is because I'm programming it in with a dial. I can figure out what the charge is on the electron. Ooh, so let's do that. Let's show this experiment. So this is what he did. He put droplets into this upper space up here. Those were slowly allowed to drip down. And then what he did was he took a device, hooked it up to the chamber, and beamed it at our particles. What did he beam? He beamed an X-ray at it. What does the X-ray do? The X-ray basically is so high in energy, whatever is on the outside of an atom gets bonked off of it. And presumably by doing that and aiming it sort of in the general direction of the oil droplets would pick up these scattered things. They would stick to the oil droplets. And then he could do his manipulation of the electric field on the dial. And so that actually worked fairly well. We're going to go and see how that worked, provided that this YouTube account has not also been terminated. It is not. That's good. All right. This one I will play the audio on because it's not bad. It is just kind of long, though. So let me resize this real quick. All right, there we go. So here's the oil drop experiment in action. It makes more sense when it's in motion.
In a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhered to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs.
All right, that's good enough for that. What does that number mean, 1.60 times 10 to the minus 19 coulombs? That is the unit of charge. We are going to use this number a little bit later on in the quarter, and then again in 163, when we talk about electricity and batteries. But this number is the coulomb. We measure charge in coulombs. So if you have a balloon and you rub it on your head and it accumulates a charge, the amount of charge that it will gain will be in coulombs. Just to quantify, like, what does that unit mean? Now, the energy coming out of your electrical socket is not in coulombs. It is coulombs per unit time. That's called the ampere. So every electron has a charge of this, 1.602 times 10 to the minus 19 coulombs. If you have multiple electrons, you have multiple of that charge. So if I had 20 electrons, it'd be that number times 20, and so on. So charge is quantized. That means that our electrons and our protons and everything operate in this fraction of charge. Now, if I play the video a little bit longer, they'll talk about how you can figure out what the mass of an electron is, and it's this right here. 9 times 10 to the minus 31 kilograms. But the important part is that these two pieces of information became known through the concept of a charged particle being ejected through the air somehow, which is from the cathode ray experiment, which then led to this. So this made the idea of an electron very, very, very popular. Everybody thought, okay, there are electrons that are on the outside of atoms, whatever that means. Like, we don't know what an atom looks like. But somehow you can remove atoms from the outside of the, or electrons from the outside of the atom, and cause them to do things. Like, you can send them flying, and they can bonk into other things, and then, so that's neat. We can manipulate them. Can we do this and use it in some other meaningful ways? And so that was where future experiments went. So the next experiment that was done, this is around like 1910, I want to say, was to figure out, okay, I know where the negative part of the atom is. What about the positive part? Because we've been doing experiments and we haven't seen a positive particle. Where is that? Where are the protons? What does the atom look like? And so a bunch of ideas were pitched. Here's the first idea. This is called the Plum pudding model. And the Plum pudding model said, okay, I have negatively charged electrons floating around in this sort of like ether, they called it. And the ether has a positive charge. It doesn't have any mass to it. It's just this nebulous positive charge. This was called the Plum pudding model because plum pudding was a popular food item back then. Think of oatmeal with raisins in it, and you have the plum pudding model. The plums, or the raisins in the oatmeal, would be the electrons, and then the oatmeal itself would be the diffuse positive charge. I don't know of many students that actually eat oatmeal. I mean, I think it's actually kind of tasty, but a lot of people are like, wow, this is disgusting. And I can't really criticize them for it. I grew up with it. I grew up in the 80s. That was what we had to eat. So I like oatmeal, but let me see if I can find a picture of raisin oatmeal for you, just in case that helps here. Raisin oatmeal. Not raisin oatmeal cookies, but yeah, there's a good picture of it. So if I do this, now everybody's just hungry. Look what I've done. But this over here, this is what I want. So you can see how this model, the raisins are like the electrons, and then the oatmeal itself is just the positive charge that floats around. So this model is not just delicious, it's totally wrong. Now, somebody came up with a different model of the atom, and it's like the Saturnian model, because you can see it looks kind of like Saturn, right? So they said, okay, well, maybe, this was Nagaoka in Japan, proposed this model in 1903. And their laboratory said, well, maybe matter is a positively charged nucleus that's really big, and then your electrons whiz around the outside like a ring. Now, the problem with this model is that electrons repel each other in all dimensions. So, oops, I have the wrong pen selected. So it'd be very difficult to get all my electrons to remain constrained on this ring. Because if these electrons repel each other, and these electrons repel each other, what's stopping them from just going in this direction or this direction, right? Why are they all stuck on this plane? So that didn't quite make sense either. Also, if we were trying to eject electrons, ejecting an electron would inevitably cause this to happen, right? I remove an electron and then everything else is repelled in all random directions until it settles back down, and it just doesn't seem likely that they would all settle into this ring. So we have an issue, and the issue is that neither of these quite work. Furthermore, what would happen if my electrons bonked off of the giant positive thing in the center that they're attracted to? So we need a better idea, and we need an experiment that will definitively determine what the atom looks like. And so in the last 2 minutes, I'm going to show you the Rutherford model. The Rutherford model did the following. It said that, okay, I have several possibilities of what my matter can look like. We're going to do an experiment to see which of these will happen. I'm going to take a radioactive source, and I'm going to beam it through a sheet of gold. And we're going to see what happens. Here's my beam of particles. It's going to look like this. And his model said, okay, here are the 3 possibilities. Possibility A. If we have the plum pudding model, where I have diffuse positive charges with electrons in the middle here, then what should happen is my particles will go straight through, and my detector will see a bunch of impacts directly through. And then the rest of my detector, which is around like this, I won't see anything else. Here's option B. If it's the Saturnian model, where here's my electrons going around the sides, my particles will hit this and they'll just bounce off in random directions. And so what I'm going to see is I'm going to see a bunch of hits in front of the sample, but I'm not going to see anything behind it. That should be very easy to differentiate. Either there's impacts beforehand or afterward. And then there's Model C. What if it's something else, and part of it passes through, and some of it gets deflected, and I see everything on the outside that I expected, but also directly through? What would this indicate? And so he said, okay, well, if we get both, depending on the number of things that are on the outside versus over here, that's going to dictate how big the nucleus is. So if most passes through, Not moss passes through. Hold on, history tool. We'll get rid of those. There we go. If most pass through, then the atom must look like this, where here's our electrons going around the outside. And the nucleus is very tiny. And it turns out of these three models, the one that was correct was Model C, which is the model of the atom that we have today. So when we come back on next week, because we're out of time for today, I'm going to show you this video of Rutherford's gold foil experiment done up with a modern touch. This experiment was actually done in 1903, or sorry, 1908, by holding up a piece of gold foil with somebody's hand and a screen with somebody else's hands, and they, while pointed at a radioactive source, so they had this radioactive substance pointed at them, basically. They turned out all the lights and closed all the blinds and observed by eye where the flashes were, and they noticed that, wow, we're getting a lot of flashes that just go straight through the detector over to here, but we occasionally get one in a random spot. Is that experimental error? No. It seems to be doing this pretty reproducibly. And so the model they got was Model C, which we have right there. There's the Model C. All right, so that's what we're going to pick up next time when we come back on a what was I going to say? Tuesday. I did not talk about your lab. I forgot to do that. Lab number 1 is pretty straightforward. It is a glassware experiment. And basically the intent of that is for you to look at the data that is presented with the glassware, calculate the density of water based on it, calculate the density of a sugar solution. We could talk a little bit about that on Tuesday, but I think it's pretty straightforward. Feel free to ask me questions about it in the Discord channel, or send me an email about it. I will put up the assignment for that. That will be due next Thursday, or whatever it says on the syllabus. I think it's Wednesday or Thursday. I'll look it up. And then quiz number 1, which will be chapter 1 content, that will be due a week from today. So that's going to be posted in just a little bit after I take down the stream. All right, so that's all I really have for today. So thanks for coming out to the lecture. I appreciate everybody showing up. Please, again, make sure that you are asking me any questions that you might have about the content. We're going to slowly start to dip into new stuff. After Chapter 2, we're going to do Chapter 6. Chapter 2 is very short. We're like already halfway done with it. Chapter 6 is molarity and stuff, and we talked about that in 140, so we'll breeze through that. And then we're going to hit Chapter 3, and we're just going to be stuck in Chapter 3 forever until like week 8. So make sure that you're staying on top of this stuff, because we're going to go pretty fast until we hit the molasses train of quantum mechanics. So yeah, that's all I got. Work on the quiz number 1 over the weekend. Make sure that you work on that lab too. Ask me any questions in Discord. Take care.